Hi, and welcome to this introduction to hydrography. I'm Stephan Howden with the University of Southern Mississippi. So the objectives of this lecture are to introduce you to the profession of hydrography, to give you appreciation for the importance of hydrography, and to give you some resources to learn further. So before I give you a definition of hydrography, let me introduce you to the International Hydrographic Organization. It was established in 1921. It's the intergovernmental consultative and technical organization to support safety of navigation and protection of the marine environment. It has UN observer status, and it's recognized as the UN competent technical authority for hydrography and nautical charting. And below, I give the URL for the organization. So here's the IHO definition of hydrography. It's the branch of applied sciences which deals with the measurement and description of the physical features of oceans, seas, coastal areas, lakes, and rivers, as well as with the prediction of their change over time, for the primary purpose of safety of navigation and in support of all other marine activities, including economic development, security and defense, scientific research, and environmental protection. So hydrography provides critical portions of the geospatial backbone for oceanography and coastal science. So what do hydrographers do? They survey the seafloor, lakes, and river bottoms. They survey the shoreline and structures of significance to navigation, for example, bridges. They take oceanographic measurements, so water levels, currents of significance to navigation, sound speed profiles, sediment samples. They utilize information from water column acoustic backscatter and many other types of measurements. They also create navigational charts, and they do other things as well. So the importance of hydrography is multifaceted. Here's a list, a partial list of important things that hydrography addresses. I'm not going to go through this list, but I want to show you some examples. So if we look at shipping, cargo and container ships rely on accurate charts. These ships move 95% of all international goods. Navigating with smaller under keel clearances makes money. This diagram taken from NOAA shows that each inch of draft can mean an extra $5 million of cargo that can be loaded on a ship. So the bigger the ships get, the deeper the draft, and the smaller the tolerances are for coming into a port between the bottom of the keel and the seafloor. So smaller under keel clearance requires more precise hydrographic data and real-time positioning. In the Arctic, due to climate change, there are new sea lanes that are being opened. So there's less sea ice in the summer than there used to be. And here's an example of a mega cruise ship that sailed through the Arctic. So the Crystal Serenity cruise ship completed a Northwest Passage Arctic journey in 2016. And so much of this water is not well charted. It's also important for resource exploitation, including oil and gas. Here's some pictures of some rigs out in the ocean, and there's a lot of this going on in the Gulf of Mexico. In this figure, these are the oil and gas production wellheads in the Gulf of Mexico. Here are the oil production platforms and the pipelines. So you can see that there's a lot of infrastructure out there in the Gulf, and and the seafloor needs to be mapped accurately to position these. Another type of resource exploitation is offshore wind farms. And so when these wind farms go in, the seafloor has to be surveyed to look for what is the type of sediment, how deep is the water. And then when these structures are put in place, there has to be further surveys to make sure that there's not scouring happening around the structures. Hydrographic surveys are also important for maritime boundary delimitation. This is an example in the Arctic Ocean. Again, as I mentioned before, in the summer, the sea ice cover is getting smaller, and that makes resources on the seafloor become available and new shipping routes open. And so there's more of a move to claim parts of the Arctic Ocean for different countries. And the boundaries for those claims depend upon charting of coastlines and where the coastlines line up with different tidal datums, which I'll get to later. Another important application is for offshore aquaculture. So offshore aquaculture, both coastal and offshore, are projected to be important to help feed a growing population. Half of all fish for human consumption now comes from aquaculture. And the food security for the growing world population will be significantly positively impacted by aquaculture. And so hydrography provides the baseline environmental data that's needed for aquaculture sightings. And this includes surveys of the seafloor, sediment type, and subsurface structure of the sediments, and if there are any objects, metal objects like pipelines or wrecks or anything like that in the area. Numerical models are used for many purposes, and the models need accurate bathymetry and coastlines in order to do a good job at forecasting or predicting how storm surges are going to be, what currents are going to be, etc. So on the left, I show a model grid and the coast, and you can see how the grid conforms to the coastline, and depths need to be set for each of these grid points. On the right, you can see an example of a storm surge forecast from the National Oceanic and Atmospheric Administration in the US. And so this model relies on having that coastline and having the bathymetry right, and that's done through hydrographic surveys. As I'll talk about later, a lot of the seafloor mapping is done with acoustics. And the water column backscatter gives information on constituents like zooplankton, fish, also density layers that are there in the ocean. And then backscatter from the seafloor gives information on sediment and seafloor habitat. So all of these hydrographic measurements have to be georeferenced. And that requires datums. And datums are the reference frames that we measure to. So some of the important reference frames for positioning for hydrography include vessel reference frames, which are used for relative positioning of sensors on the vessel, ellipsoidal geodetic systems frames, which are traditionally used for horizontal positioning on the Earth. They give us the latitude and longitude and are the basis for 2D map projections. And then more modern geodetic datums, which are used for 3D and 4D positioning. 4D adds in the component of time because there's a lot of seafloor and continent movement, et cetera, in time that has to be accounted for. There are orthometric datums, which are based on the geopotential of the Earth, and they're traditionally used for vertical positioning, and I'll show diagrams later. Tidal datums, which are based on sea level measurements and tidal stages. These are used for vertical positioning and also for horizontal positioning for many boundaries. And then there's other types of reference frames like specialized vertical datums for vertical positioning on lakes and rivers. So here's an example of a vessel reference frame. So on the top left, you can see some people who are doing a survey of a vessel. So they're using land surveying equipment to survey the locations of things like GPS or GNSS receiver antennas, multibeam systems, inertial measurement units that are on a survey vessel. And when they're done, they have a vessel coordinate system that gives the relative locations of all of these sensors. Before I talk about geodetic datums, I need to say a few words about the geoid. The geoid is the equipotential surface of the Earth's geopotential that best fits global mean sea level. It would coincide with mean sea level if there was no external forcing or geostrophic balance in the ocean. So the figure below, the first figure, shows an idealized Earth with the geoid and then equipotential surfaces of various values as we move away from the Earth's surface. Now, since each of these contours is a constant geopotential, the gravity vector at each location is normal to the surface of the geopotential. So what that means is that plumb lines are curved because of this ellipsoidal shape of the geoid in the Earth. Or near the equator and the poles, we have these curved plumb lines that are lines that pass through successive geopotential surfaces at right angles. The figure below shows a modern geoid from an Earth gravity model provided by the European Space Agency with exaggerated relief from a pure ellipsoidal shape. And the topography of this geoid relative to an ellipsoid is about plus or minus 100 meters. So now we can look at geodetic datums. So historically, the Earth was recognized to be closer to an ellipsoidal of revolution than a sphere. And that shape is due to the fact that the Earth is spinning on its axis. So in the Earth frame of reference, there's a centrifugal force that causes the equator to bulge out. And so the intent with these ellipsoid Earth models was to have them aligned so the semi-minor axis, the short axis, is aligned with the spin axis of the Earth. The semi-major axis would be along the equator. And then the size of the ellipsoid would be such that it would fit the geoid. And prior to satellite navigation, the ellipsoidal fits were done to either national or regional land surveyed networks with celestial observations. And so these first two figures show an exaggerated view of ellipsoids that were fit to a local, a national, say, and a regional network, where the semi-major axis was not parallel to the spin axis of the Earth, and the semi-major axis was not well aligned with the equatorial plane of the Earth. And the shape of the ellipsoid didn't really fit the global geoid, but it fit the local survey network well. Then with the modern space geodesy and positioning, a better ellipsoid has been determined that best fits the mean Earth geoid. So some places the ellipsoid is below the geoid, some places it's above the geoid, but over the whole surface of the Earth, it's a best fit. And the semi-minor axis is well aligned with the mean spin axis of the Earth, and the semi-major axis is well aligned with the equatorial plane. And it's this geodetic model that gives us our latitude and longitude, which we use for horizontal positioning. So in the figure in the middle below, you can see a Earth with these graticules. So lines of constant latitude, lines of constant longitude. We have a prime meridian where longitude starts at 0 and latitude starts at 0 on the equatorial plane. In Africa, the modern geodetic datums used include the World Geodetic System, 1984, and the new relatively new African Geodetic Reference Frame. Now it's important, because there are these different geodetic datums, a really important point is that a given location on the Earth can have different latitude and longitude if it's using a different geodetic datum. And just to illustrate this, I took this picture from a book by Nigel Calder on how to read a nautical chart. And what it shows is two charts, and there's a harbor. And you can see on both charts, there's a line of constant longitude and a line of constant latitude, and they cross. In the top figure, they cross in the harbor at one of these piers. In the bottom figure, it's the same area, but it's just with respect to a different datum. And that same line of constant latitude and line of constant longitudes intersect at a different physical location. So if you were using one of these charts and you say you're using an electronic navigation system like GPS, and you were using a different datum to navigate than the chart was, and it was foggy out, you might run into a pier in this case. So another important datum is orthometric datums. And again, this is related to the geoid. Orthometric heights are heights above the geoid following a vertical tangent path to gravity vectors. This is commonly used for terrestrial elevations. So in this figure, you can see the mean sea level out here. You can see the geoid, and it's tracking close to the mean sea level until you get in this region here where it's close to the continent. And then the same equipotential surface taken into the Earth. And in the green is the global ellipsoid model of the Earth. And so there is a point of interest here on the topography. And the orthometric height is roughly the height of the point above the ellipsoid plus the geoid distance to the ellipsoid. And there's a similar to, or not quite equal to, sign here, because you can see that a normal to the ellipsoid, which is normal to this ellipsoid shape here, is a different path than if we followed a plumb line to the geoid. So there's some subtleties here we have to worry about. Tidal datums are another important type of vertical datum in hydrography. There are many different types of tidal datums, and they are generally defined over particular time periods or epochs, because when we take means of stages of water level, that can slowly change over time. And there may be high frequency changes in sea level, and we need to average over those. So we have to have a minimum time and a maximum time. Minimum time to average out fluctuations that are higher frequency than tides, and a maximum time period to take into account the fact that there may be a long-term drift in any of these datums. So the figure to the right shows a vertical cross-section with different tidal datums. And so we have the sea level at a given time, and we have a range of the sea level when we have spring tides and when we have neap tides. And I'll show you in the figure below what that means. We have a stage of the tide, a mean stage, so the mean high water springs, which is the mean high water during spring tides. We have a mean high water neaps, which is the mean high water neap. We have a mean low water neap and a mean low water springs. And then finally, we have the lowest astronomic tide. And that's the chart datum that's recommended by the International Hydrographic Organization. So down below, just to illustrate some of this terminology, here is a 60-day record, a little over 60 days of tides from San Francisco, California. And this is a mixed semidiurnal tide in this region. So we have 2 highs and 2 lows a day. And you can see times when the range is larger and then times when the range is smaller. When the range is larger, those are called spring tides. And when the range is smaller, it's called neap tides. And as Dr. Arbic talked about in his tides lecture, the spring tides occur when the sun, the moon, and the earth are approximately in a straight line. And the neap tides occur when the sun, the moon, and the earth form approximately a right angle. So during the spring tides, the tidal forcing due to the sun and the moon add together, and during neap tides, they work against each other. Vertical datums for soundings are termed chart datum. And on a chart, for vertical datums, you generally have a chart datum, which is what's used for the soundings, and then another tidal datum for overhead obstructions. So some examples of chart datums are lowest astronomic tide, which, as I mentioned, are recommended by the IHO. And it's the lowest predicted tide from harmonic analysis. Another example is mean low water springs. And in the US, we use mean lower low water. Now, tidal datums require tide gauges. There are national and international networks of long-term tide gauges that can serve as primary gauges for hydrographic surveying. If more tide gauges are required for a hydrographic survey, then secondary stations are installed for the length of the survey, but generally not less than 30 days. And that's one of the requirements for an IHO survey. In some cases, known tidal harmonic constituents and or tidal modeling are used to obtain chart data in a region. So some of these resources for international sea level data include the Global Sea Level Observing System, or GLOS, and here's the URL for it. The Permanent Service for Mean Sea Level, the University of Hawaii Sea Level Center, the British Oceanographic Data Center, and sea level station monitoring. So you can go to any of these websites. The main one to go to would be the Global Sea Level Observing Center. And each of these, when you go to GLOS, you will see how these different water level data centers are organized. So some of them is for the long-term data, the highest quality control. Then there are others for more real-time data. If you're doing a survey and you need to add additional stations, you have to install the secondary gauges. And so here's some photographs of some students that I taught putting in a temporary tide gauge. So they have to install the water level instrumentation. In this case, it's a pressure sensor, two different pressure sensors, a water bubbler and a piezoelectric crystal. So the figure on the right shows the data logger. The figure on the bottom left shows an installation of the tide staff with the pressure sensors on it. And then there's two other pictures of surveying the tide staff with the pressure sensors into a set of benchmarks. So here are the primary methods of hydrographic surveying. This is not an exhaustive list, but these are the main methods. So lead lines, which is an old method, you have a weight on the end of a rope that's got markings on it, and you measure how deep the water is. Currents can move the, have drag on the rope and give you an inaccurate reading. So then acoustic methods were developed. So first single beam echo sounders and then multi-beam echo sounders. There's also airborne LIDAR, which stands for light detection and ranging, and then satellite radar altimetry, which does not provide bathymetry to IHO specifications, but provides data where no other is available. So it's really important. So here's a diagram showing mapping the sea floor from the lead line to the multi-beam. So lead line is pre-1940. Single beam echo sounders were from the 40s through the 80s, and they're still used in some cases. So you just have a single beam that you're measuring the depth below the vessel. And then multi-beam, which started in the 1990s, where you have multiple beams that you're measuring. You have a swath of measurements of the seafloor. So both the single beam and multi-beam systems, because they rely on acoustic two-way travel time, the speed of sound is really important to monitor. Here's a movie of multi-beam surveying from NOAA. So the ship's going along, and the swath of the multi-beam is mapping the seafloor below the ship to either side. So you get a lot more information than just a single beam echo sounder. Now in a traditional survey, in this diagram on the bottom is more illustrative of a single beam echo sounder, but the same principles apply. You have a vessel, it's in the water, there's a water line on the vessel, there's an echo sounder at some depth below the water line. And so it takes a sounding, there's a round trip travel time of the sound pulse. You divide that by 2 and multiply by the speed of sound, and you get the depth below the transducer. You add the transducer depth to waterline, and you get the depth of the water at that point. But for a nautical chart, what you want to know is the depth of water below the chart datum, whether that be mean or low water or lowest astronomic tide. So you have to know something about, at the time the sounding is made, where is the water level with respect to that chart datum? And for that, you need water level information. So you need tide gauges and you need tidal zoning, which gives you information on how the tide varies in the survey area away from the tide gauges where you're actually measuring the water level. There's other complicating factors. There's vessel heave. So there's waves, surface gravity waves, and the vessel can move up and down. And so it's not maintaining a mean water level. And that can be mitigated with a low pass filter. Also, there can be vessel pitch and roll, and that can be measured and removed if necessary. With multi-beam systems, it can be removed through beam forming. There's also vessel squat, which can be measured and removed if necessary, and vessel dynamic draft. And again, it can be measured and removed. And then there's sound speed variations, and which cause refraction, or any sound waves that are not incident at a normal angle to sound speed isolines. So the way you mitigate that is to measure sound speed profiles. Now, a more modern way to get away from that tidal zoning and measuring the vessel heave and the squat and the dynamic draft is what's called an ellipsoidally reference survey. So we decouple the tides from hydrographic survey. And this diagram illustrates how that works. So we have a reference ellipsoid. In this figure, the reference ellipsoid is above the water level. In some places of the Earth, it'll be below. And there's GPS, or GNSS for Global Navigation Satellite System. So there's a receipt antenna on the top of the ship here. And it's continuously measuring the height of the antenna from the reference ellipsoid. Then there's a measurement from the vessel configuration survey of the antenna to where the echo sounder is. And the echo sounder is measuring the soundings. So this blue height, or depth you may want to call it, of the seafloor from the reference ellipsoid is found by adding the ellipsoid height of the antenna, plus the antenna lever arm, plus the sounding. And if the ship moves down, it would say there's heave. If it moves down in the water, the sounding will be smaller, but the ellipsoidal height will be bigger. So we still get an accurate measure of the height of the seafloor from the ellipsoid. So water depths are measured to the reference ellipsoid. The separation, the SEP here, from the reference ellipsoid and the chart datum may be determined by others. For example, in the US, the National Oceanic and Atmospheric Administration has a tool called VDatum, where they've created this separation between the ellipsoid and tidal datums through tidal observations plus tidal modeling. And a hydrographer can use that tool to reduce their soundings to the ellipsoid to soundings from chart datum. Another way of mapping the seafloor that's commonly used is from airborne LIDAR. And the figure on the left illustrates how that works. There's an aircraft, and it measures, using a laser, the distance to the sea surface and the distance to the sea floor, and by subtracting those, can get the depth of the water. So this type of measurement also requires that the water level to chart datum be known somehow. In this case, it would need to be a traditional tidal zoning applied to correct that depth, that raw sounding to a sounding with respect to chart datum. In addition to the depth of the water, the hydrographer has to measure the shoreline, aids to navigation, and overhead obstructions. So the shorelines and aids of navigation can be done using traditional land surveying techniques, and also putting GPS receivers, holding them up to the ATONs and getting coordinates that way. But LIDAR surveys on the ships are becoming an efficient way to survey the shorelines, ATONs, and overhead obstructions. So on the bottom left, this is a LIDAR system on a USM survey vessel. And on the right, you can see the picture of a bridge from this LIDAR system. And these points are all georeferenced. And on the bottom, you can see aids to navigation that were surveyed with the LIDAR system. And again, they're georeferenced. As I mentioned before, where there's not good hydrographic data in the world's ocean, satellite altimetry can be used to estimate the bathymetry. And so satellite altimeters have a radar that measures the sea surface, and it can be referenced to the ellipsoid. So we get sea surface to the ellipsoid. If there's a seamount in the ocean, the seamount is going to be denser than the ocean above it. So if we were to measure, if we had a gravimeter and we were measuring gravity, acceleration due to gravity, and its direction, if we were far from the seamount and the ocean floor was homogeneous, then the gravity vector would look like this black vector on the left. So it's perpendicular to the sea level. As we get closer to the seamount, the gravity vector is going to start pointing towards the seamount because it's denser than the ocean. So there's more mass in that volume than there is where the ocean is. And so because that vector is going to be pointed towards the seamount, and we know that vector is perpendicular to a geopotential surface, then it means the geopotential surface is also going to slope up above the seamount. And then as we cross to the other side, it's going to point towards the seamount again, and it'll slope the sea surface. If it's following the geopotential, will slope down. So from the satellite altimetry, we can estimate seamounts and also canyons on the seafloor. Now, it only works for certain sizes of seamounts and canyons or trenches, but it still provides very valuable information. As an example of how important it is, there was a US submarine accident where a submarine struck an unmapped undersea mountain. And it turned out that in the satellite altimetry data, the mountain was visible. And this is a figure of the ocean bathymetry from satellite altimetry that shows seafloor features, that some of which were not mapped using multibeam or single beam echo sounders. So we've looked at the primary methods of hydrographic surveys, and additionally, we looked at satellite altimetry. So for the hydrographic surveys, where do the standards come from? So the IHO has set standards for 5 orders of surveys that are focused on surveys taken to create or update nautical charts. National governments may set their own standards. Many times they use the IHO standards, but there's some applications where they don't use them. And private clients, of course, can set their own standards as well. So if you go to the International Hydrographic Organization website, there are publications, and one of the publications, if we go to standards and publications, is S44, which is standards for hydrographic surveys. So this is the latest edition. It's edition 6.0. And as I mentioned, there are 5 categories of surveys. So the less stringent requirements, the lowest requirements are for order 2, and increases for order 1B, order 1A, special order, and exclusive order. There's a table in S44 that describes the minimum standards, bathymetry standards, for safety of navigation hydrographic surveys. So on the left is order 2, and over to the right is exclusive orders. So we have the different criteria. And if we look at depth, there is a total horizontal uncertainty. So how well those locations of soundings are determined with respect to latitude and longitude. And if we start at order 2, that's 20 meters plus 10% of depth. And if we get up to exclusive order, it's got to be within a meter. Then there's total vertical uncertainty. So all the uncertainties that go into determining the depth of the water with respect to chart data. And there's a formula that's used, and there's a couple of coefficients. There's an A coefficient and a B. The lowest order, order 2, A is 1 meter and B is 0.023, and we get to exclusive order, A is 15 centimeters or 0.15 meters, and B is 0.0075. And there's some other requirements as well. But so we see that the total horizontal uncertainty and the total vertical uncertainty decrease as you go from order 2 to exclusive order. Let's look at some new directions in hydrography. So there's new techniques and technologies for shallow water mapping. That includes drones, and they can have digital cameras and use structure for motion to bathymetry. And also their compact LIDAR systems. So on the top right, I show a Regal Bathycopter, which is a copter drone with a LIDAR system, a lightweight LIDAR system below it. There's also citizen science and crowdsourcing. So there's all these boats taking soundings with their depth sounders. And though they may not be as accurate as a hydrographic survey launch, if you aggregate a lot of data, you can average it and do some quality control and get important information where you may not have enough. Another new direction is uncrewed vessels, and here I show 3 examples. The first is the sail drone. It's a sailing drone, just as its name implies, and it can stay out for long periods of time because it's using the wind for propulsion, and it's got some solar panels to recharge batteries. And they've made a bigger sail drone model now that has a generator so that it can run equipment even if the solar panels are not charging up the batteries sufficiently to run the equipment. And then here's the IX Blue Drix, which is an uncrewed survey vessel. So it has a multibeam below the water, and it can go out and map the seafloor. Here is the L3 Harris Seaworker 5, which is another type of uncrewed vessel. So the Drix and the Seaworker 5 both have They both have engines to run propellers and for charging batteries. So in summary, hydrography provides the geospatial framework for oceanography and coastal sciences. Hydrographic surveying is moving from being focused on mapping the seafloor for nautical charts to exploiting all the information in the backscatter from the seafloor and water column for multiple uses. The new mantra is map once, use many times. And I showed some examples of that earlier on, like the water column backscatter for fisheries and zooplankton, the seafloor backscatter for habitat mapping. And also hydrographic practices are evolving along with the technology. So before I end, I want to mention Seabed 2030. So this is a collaborative project between the Nippon Foundation of Japan and the General Bathymetric Chart of the Oceans, or JEBCO. And the focus of this is to have 100% of the ocean floor mapped by 2030. And this has been selected as a UN Ocean Decade action. So this is the website where you can go to for the Seabed 2030 initiative. And this is not a funding mechanism, but it's a data aggregator and meant to spur organizations to fund more mapping of the world's ocean. So having 100% of this ocean floor map means having multi-beam mapping of the entire ocean floor by 2030. Okay, here's where I'm going to end, is further resources. So a great resource is the IHO website. And there's many publications there that include how to do hydrographic surveying. And one of the publications is C47, which lists training courses in hydrography and nautical cartography. So if you go to this URL, you can upload a listing of those if you're interested in attending training. Some of the training involves academic programs where you also get an academic degree, and some are just certificate programs. Another good resource is the NOAA Office of Coast Survey in the US. Here is the website for their publications. And again, they have many publications on standards, how to do requirements for hydrographic surveying, manuals on hydrographic surveying. And then finally, the University Corporation for Atmospheric Research, or UCAR, has the COMET program, and there is a short course on Introduction to Hydrography that you can go through. So this isn't an exhaustive list of resources, but it's a great set to get you started if you're interested. So thank you, and if you have questions, I hope you can come to the question and answer session that I have and just look on the schedule for when that's going to be. Thanks a lot. Bye.